Hello. Hello all. I'm Mr. Kole. Today I'll be talking about our work on columnar liquid crystalline phases of active matter. This is a work that was done in collaboration with my co-advisor Gareth Alexander at Warwick, Ananya Moitro at Sir J. Paris, and Sriram, my advisor at IISc. Active matter, as we all know, it's a collection of self-driven particles, and these self-driven particles move in an ambient medium by exerting stresses. A classic example of such a system is collection of swimmers. More often than not, you see that such swimmers form a orientationally ordered state, and due to these intrinsic stresses, they exhibit dynamic instabilities. If you think for some time, you'll realize if you have a translational elasticity, then such instabilities can be inhibited. For example, if you see this cartoon, so if you see the cartoon there, which shows a lamellar phase, you can see a bend stability of the form will be resisted because of the translational elasticity in 1D, while for a collection of columns in this, you see the splay instability will be resisted because of 2D translational elasticity. Now, so if you have a combination of a liquid and a solid-like directions, as you would see in, say, smectics and columnars, then it's best of both the worlds. So past the instability, you can control the flows and guide them if you have such a system. I mean, so for a biological example of a columnar phase would be motor microtubule bundles in axons. So you see this is microtubules on which the motors act, and so the system is active, and of course it's chiral. So the systems that we'll be looking at is columnar phase. So you have to think of them as disconnected units. They don't have shear modulus for shearing along the columns, but a slice of it has 2D translational order. It's a crystal. So for an isotropic system, you will have two lambda coefficients, lambda and mu, with the energy cost for column bending given by kappa. E here is a nonlinear strain tensor, which would be symmetric part of the gradients of u and grad u piece. Now, chirality, as we know, is if an object cannot be superimposed on itself, its mirror image, then the object is said to be chiral. For equilibrium phases, you see that the chirality is not so, I mean, equilibrium systems, you don't see chiral effects so far as the mechanical and hydrodynamic properties are concerned. If you have systems which are chiral and active, and say they have broken translational invariance, then interesting effects like odd elasticity appear. This was studied by a group in Chicago, Vincenzo Vitelli, where they studied a spinner fluid, and realized an odd elasticity. Odd because the response of the system is in the perpendicular direction to the displacement applied. While we studied in this work last year, active cholesterics, which have order elasticity, more of which can be read there. So to understand this, we have a framework, generic field theory, we're composed of a pseudoscalar field because we are working for chiral systems coupled to a velocity field, and which will specialize to a two-dimensional condensate, that is the columnar phase, which will have a 2D reciprocal lattice incorporating the displacement field u bar. Hydrodynamics essentially deals with stresses, so we'll have both achiral and chiral stresses. The one in the coefficient with red is the achiral stress, and the chiral stress is the one with zeta c. This is the term that breaks the inversion symmetry. So without going into the details of the algebra, let me flash the equations of motion. So this is a system which is an apolar. So you have columns, and it's up-down symmetric along the z direction. And we ignore permeation. So basically, it's a kinematic equation of the displacement field, that is delta u per is v per. And we look in the Stochastian limit, which is eta delta v will be forces coming from stresses. So contributions from the elasticity lambda and mu, which is mildly affected by the activity. And importantly, you have a contribution which is of the form tilt modulus of the columns. This would be absent for an equilibrium columnar phase. As told before, zeta is the term that really breaks the time reversal symmetry, that is the activity, and zeta C breaks both time reversal symmetry and inversion symmetry. So let's look at just the achiral effects. Yeah, let's look at a system which is achiral, bulk achiral. Then such a system, if you have extensile activity, that means we are pushing on the system, that would undergo a buckling instability. Now these are columns, so they would form a helix. Now this is a form of a spontaneous version of chiral symmetry breaking, because it was straight, now it's buckled, there is a helix, it has a particular chirality. So it's a spontaneous version of chiral symmetry breaking, which has a similar structure as you would see in the Hilfrey-Shiro, well-known Hilfrey-Shiro instabilities of columnars or smectics. The systematics is the same. If you have chirality on top of this, then you see there are these very interesting flows, which, as shown in the figure, the red arrows, you see that the velocity profile goes round and round along the z direction and in a manner of a cholesteric director field due to the rotations in the plane and spatial variations in the tilt of the columns. As I said before, so the interesting fact about such translationally broken translational invariant systems is that you can have an effective free energy like description. That is, you can map an active system, say of a lamella phase or this columnar phase, onto an effective free energy description like system, where if the system is extensile, then you can prohibit the instability by pushing onto it in the plane. So this can help you measure the activity and also control the active effects. Furthermore, we look at a system which has polar symmetry, that is along the z direction. There is a special direction along the z. So z and minus z are not equivalent. Here there is an interesting effect that apart from the achiral terms, the chiral terms are of the sort that I talked before, that is 2D odd elasticity, which essentially means that if you have a system, say u perp is the displacement in one direction, then your velocity flows will be in perpendicular direction. That's the response in the perpendicular direction to it. So for such a polar system, you see that the symmetry is broken. They undergo this helical instability, and there are these flows. Now, because there is this symmetry broken, then you can have a material transport along the column axis. So it's like a viscous Archimedean screw. It's a spontaneous version of viscous Archimedean screw. Yeah, so I'll conclude. I hope I've convinced that the active hydrodynamics of columnar phases is surprisingly rich. I talked about spontaneous version of chiral symmetry breaking, that is the helical instability. I told about the odd flows and also the connection between the externally imposed stress and activity. I talked about the polar columns where the in-plane 2D elasticity is the old odd elasticity and the realization of viscous Archimedean screw. Future directions which we are working on is flows and defects in such systems.
Thanks, SJK. Questions?